So I'll be giving a little bit of a background on MySQL HeatWave and then getting into the details of the scale-out data management aspect, which was recently introduced. So MySQL database service with HeatWave was introduced or launched last December. And with that, this becomes the only MySQL-based service where you have a single database which can efficiently process both transactions as well as complex analytic queries. In the past, customers would need to move data out of MySQL database into some other database. But now there can be a single database and no need for any ETL, and customers can run both their OLTP as well as analytic applications. The advantage of not requiring two databases is that customers don't need to manage two different databases with two different semantics, for one. But the second thing is it obviates the need to move the data so that all the data is in one place, which is MySQL. So any changes which are made by the transactions are visible to the complex queries right away. One of the other advantages of this approach is that we have enhanced the MySQL optimizer to integrate HeatWave. As a result, all tools and applications which are compatible with MySQL continue to work without any change. And this is one of the reasons we are seeing a lot of migrations from Aurora, because Aurora is API compatible with MySQL, and customers can migrate their applications very seamlessly. The system has been designed for massive scale, and it scales to thousands of cores, and we will talk more about the scalability aspect in depth today. Given that this is a query accelerator, the first question is that, okay, how is the performance of HeatWave compared to some other services out there? So HeatWave is Oracle Cloud's innovation over MySQL, right? So we took MySQL, enhanced it with a bunch of cool technologies, and we're offering that as MySQL HeatWave in the Oracle Cloud. Similarly, Amazon has taken the open source version of MySQL. They have made some enhancements like parallel scans and such, and they're offering that as Aurora. So the question is, how did the two products compare? Well, we ran a 4 terabyte workload. So this is like a 4 terabyte TPCH workload. The first thing we observed was that there is no need to create any indexes with HeatWave. HeatWave is an in-memory engine, so we don't need to create any indexes. Whereas with Aurora, we need to create indexes. So on 4 terabytes, it took about 120 hours, like 5 days, to complete creating the indexes with Aurora. Whereas with HeatWave, the system was available right away to run queries, right? So if you think about the availability of when the system is available to run queries, HeatWave is a lot more available than Aurora, just for that simple reason that no need to create indexes. But in any case, we created all the appropriate indexes and optimized Aurora so that it uses all the appropriate features. After doing so, when we ran the 22 queries, on an average, a query took little over 2.5 hours with Aurora. In contrast, an average query with HeatWave took 6.3 seconds, right? So 2.5 hours versus 6.3 seconds. This is a dramatic improvement in the customer experience when they use HeatWave over Aurora. Not just that, not only is it the case that HeatWave is so much faster, it is also the case that HeatWave is much cheaper. And this is at half the price of Aurora. So HeatWave is half the cost of Aurora, 1,400 times faster for a net aggregate of 2,800 times better price performance on 4 terabytes. If you have a larger data size, this performance improvement will increase. If you have a smaller data size, this performance difference will reduce, right? So depending upon the data size, we chose 4 terabytes because that's very representative of the data sizes we have seen from customers using Aurora or RDS MySQL. The second comparison to draw is with RDS MySQL. Here, Amazon has taken the open source version of MySQL and they are hosting it as a managed service. So what is interesting is, compared to RDS MySQL, HeatWave is 5,400 times faster, same benchmark, right? And same characteristics, that no need for indexes with MySQL HeatWave. With RDS MySQL, you need to create and maintain the appropriate indexes, which takes some time. After that, an average query takes more than 11 hours, whereas an average query, PPCH, takes 6.3 seconds with HeatWave. The fact that HeatWave is so much faster is not a surprise. We are expecting that. That's what, because HeatWave is a accelerator. What is very surprising is the cost differential. Given that RDS MySQL is just open source version of MySQL being hosted in AWS, even then, Amazon is charging you more for just hosting an open source MySQL version, as opposed to with HeatWave, we are offering you a lot of innovations, much better performance, and at a lower cost. Plus, the service is managed and developed by the MySQL engineering team. So you know that if there are any issues, you always get the latest and the greatest fixes. So this is a very important point to realize, that when we are talking about, say in the previous slide, when I was comparing with Aurora, Aurora is on a 5.7 version of MySQL. So they don't even have many of the capabilities which are in the current 8.26 release, right? Whereas with MySQL HeatWave, you're always on the latest version of the MySQL database. The service is being developed, managed, supported by the MySQL engineering team. So you get premier support. And it is much faster and it is much cheaper. It's difficult to beat this. So these two comparisons, Aurora and RDS MySQL, they are relevant because this is for customers of MySQL who want to consider which is the right platform, right? Because they can use any of these, MySQL HeatWave, RDS MySQL, or Aurora without any change to the application. So that's why it's one data point and one comparison. But for the most part, customers of MySQL who want to run complex queries or who want to run analytic queries don't end up using MySQL for it. They end up moving the data to a specialized database, which has been designed for one thing and one thing alone, which is analytics. The two most popular services for analytics are Redshift and Snowflake. So they don't do transactional processing, right? It's only for analytics. So now let's compare what is the performance of MySQL HeatWave, which can do both, right? MySQL Heat can do transactional processing as well as analytics. So now let's compare what is the performance of this generic MySQL HeatWave with the specialized offering for analytics, starting with Redshift. So this is comparing with Redshift Aqua, which is the latest and greatest version of Redshift. And this is on a 10 terabyte PPCH and run by a third party. Here we find that HeatWave is 7 times faster at half the cost. So even as an application or a user, you're willing to move the data to a different database. You're willing to maintain these two different databases with different semantics. Your data will not be real time because there's this latency involved and such. There's a cost associated. Even though you're willing to take all of the stuff and this database does only analytics, even then, you'll find that Redshift is twice as expensive and 7 times slower than MySQL HeatWave. So why would anyone want to use Redshift over MySQL HeatWave? Right? So this is the first comparison of a specialized database, Redshift. Now the next comparison is going to be with Snowflake, right? Because there's a lot of talk about Snowflake, like having a lot of good technology and such. Well, when we do the comparison, same benchmark, this is the 10 terabyte TPCH queries, right? We find that HeatWave is 7 times faster at 1/5 the cost. Now, which leads to 35 times better price performance. So if you in the cloud are running a workload, what it means is if you're going to pay as you go, it's going to be 1/35 your bill. Right? Now, for the most part, customers may have an annual contract or a monthly flex, so which is why we are showing both these things. But 35 times price performance is really like the meter, right? So you're going to be much better off with MySQL HeatWave in the Oracle Cloud. Now, the reason it's very important to show the performance along with the cost is because you can configure a different shape, a different cluster size with either Redshift or with Snowflake or with MySQL HeatWave to achieve different performance, right? So what we are showing is that for this setup, which is going to cost you 5 times more with Snowflake compared to HeatWave, Snowflake is going to be 7 times slower, right? So 5 times more expensive, 7 times slower. Now, if you were to have a smaller cluster size of Snowflake, the cost differential may reduce, but so will the performance. So the performance, instead of it being 7 times slower, Snowflake will be much slower if you have a smaller cluster size, right? That's why it's important to show both the performance and the cost together. So with all the vendors we have and all the services we have run benchmarks against: Aurora, RDS MySQL, Redshift, Snowflake, HeatWave is significantly faster and significantly cheaper. Now, the other thing to point out is with HeatWave, there is only one shape to choose from. Whereas with Amazon, if you're going to use Aurora, there's a whole plethora of choices, and the onus is on you as an application to figure out which is the right shape. With RDS, again, multiple options to choose from. With Redshift, again, multiple options to choose from. So it's super, super complicated. And most of the times, customers are going to end up with a suboptimal choice, which is going to cost them quite a bit, which is one of the reasons we introduced Autopilot, which completely obviates the need for the user to guess, right? So we have only one shape, and then we have also Autopilot. Right? So this is about the query performance, and these are on data sizes which we could handle like in the past since GA. So the question is that how are we able to achieve this dramatic improvement in performance and such lower cost? Well, there are 4 things we have done. First thing is HeatWave has been designed from the ground up for scale-out processing, meaning it's not the case that we have just taken some code and we are hosting it in the cloud. We have actually designed HeatWave for the cloud for massive scalability. And we'll talk about this quite a bit today. The second thing is it's been designed to use cloud services, which are a commodity, which are the least expensive. So for instance, we use Object Store instead of locally attached SSDs to reduce our cost. We use standard Ethernet. We use AMD-based VMs. We don't use Intel because they're a lot more expensive. The service has been optimized for OCI. For instance, we use flex shapes. That's one of the reasons we are able to offer such low cost. We determine what is the underlying cache size for these machines and partition our data in memory so that it can fit the cache. And finally, we have pervasive use of machine learning throughout the stack. And we talked quite a bit about Autopilot in the last series. We were talking about all the innovations we have done around using machine learning, both in this engine as well as in the service. As a result of these design points in HeatWave, it results in a service which is very performant, very scalable, very low cost, and highly automated. So today, for pretty much the rest of the session, I'm going to focus on one aspect, which is the scale-out processing. That what have we done recently? Basically, the announcements in a couple of weeks back compared to like our GA service, right? So the system was already very scalable when we went GA, and now we have introduced a bunch of features which make it even more so. When we talk about scalability, there are 2 aspects. One is about the size of the data you can handle, and secondly, how efficiently you can handle. And for data management, there could be 2 dimensions again. One is in terms of capabilities. One is how efficiently do we manage the data? For instance, how efficiently can we load data? Can we, anytime like you need to process data, so how efficiently can we manage the data? And the second dimension is how efficiently can we process the data for queries? So I'm going to cover these 2 points today. So the first thing is that as a part of the announcement we made on August 10th, we introduced the HeatWave cluster, which can support up to 64 nodes. So in the past, we were supporting 24 nodes, which could process 12 terabytes of data. Now, the larger size of the HeatWave cluster can be up to 64 nodes, which can process up to 32 terabytes of data. Now, when we say that the system can process up to 32 terabytes of data, what it means is, okay, we can run queries on 32 terabytes of data. But now that we are talking about a lot more data, we also have to think about techniques so that the management of this data within the HeatWave cluster can also be efficient. So let's talk about that. When the user has some data, and let's assume the data is in, say, some CSV format or a MySQL shell dump format, The data through a variety of mechanisms is ingested into the MySQL database. So you could have the data in a CSV format, you could have it in a MySQL export format, and using one of many mechanisms, the data is inserted into the MySQL database. Now, this operation is usually done once, right? When you're migrating data from somewhere else to the MySQL database. The operation which is done fairly frequently is to load data from the MySQL database, which is a persistent store, into the memory of the HeatWave cluster. So HeatWave is a in-memory engine. Right? So when you shut down the HeatWave cluster, the data is gone, and you have to read the data, and you read the data from the MySQL database. Right? So the point is that loading of the data into the MySQL database is usually done once, and then loading of the data from the MySQL database into the memory of the HeatWave cluster, that's done fairly frequently. And there are a variety of operations which can result in a reload. One is, as I said, restart, that you may want to shut down the cluster and then restart. You have to reload the data. Second thing is there could be an error in one of the nodes, right, or a fault. When you have a cluster of this size, the chances of failure increases. And even if one node has a failure, you have to reload the cluster. Third is whenever you're doing an upgrade, right? So variety of operations. So this operation is done fairly frequently. Now, what would happen so far is anytime there was a need to load data into the HeatWave cluster, the HeatWave nodes would reach out to the MySQL database or to the MySQL node to start reading data. And that would become a choke point, right? Because there's a single instance, there's a single node of MySQL database in reloading the data. So in order to alleviate this choke point, what we have introduced is the HeatWave storage layer. The first time when data is loaded from the MySQL database into the memory of the HeatWave cluster, a copy of the in-memory representation is made to the object store. So the first time when we are reading, sure, we have to go and read it from the MySQL database to the memory of the HeatWave cluster. That in-memory representation is also persisted in the object store, and it is then managed by the HeatWave cluster. So we write it to the object store, we create an abstraction so that whenever we need this data, the MySQL cluster can fetch it back. Not just that, if there are any changes which are made to the MySQL database, those changes get automatically propagated to this object store without any human intervention. And this is done by using MySQL Autopilot. So this whole process of when should we propagate the changes from the MySQL database to the object store is done using machine learning. Now, please note that the data from the MySQL database to the memory of the cluster for query processing, that's propagated instantaneously, right away. But I'm talking about the object store. That propagation is done using some machine learning logic, and we will talk about that later today. So first time when you're loading the data, not only does it populate the memory of the HeatWave cluster, but it also makes a copy of this data in the object store. This has very interesting characteristics. For one, whenever we need to load the data again, right? So which is the reload. So whenever you need to load the data again, we don't need to go to the MySQL database. We can load it from the HeatWave storage layer. And when we are loading it back, since it is in the same representation as the in-memory format, there is no need for any transformation. You can read the data at a very, very high speed because you're reading the data, you're reading the bytes as is, and populating it into the memory without any transformation. The second thing is the amount of parallelism we get is very, very high, right? So there are multiple nodes and they can all read the data in parallel. And this leads to a very interesting property. So take this first example where there's one node attached and one node can process about 400 gigs of data. And we see the amount of time it will take to load the data is 400 divided by the bandwidth of the object store. Now let's assume there are 4 nodes connected, right? There's a HeatWave cluster of 4 nodes. Well, now if you want to load 4 times 400, which is 1.6 terabytes of data, all these 4 nodes are reading in parallel, and you have 4 connections to the object store. So again, the amount of time it's going to take is 400 divided by the bandwidth. Similarly, if you have any number you could have 64 nodes cluster, and the 64 node cluster is reading your about 32 terabytes of data in parallel. The time it'll take is still 400 divided by B. So what this shows is with this scale out architecture, and that's why they named the scale out, is that the load time depends only on two things: the amount of data per node, which we know is about 400 gigs, and the object store bandwidth. So this is a very interesting property that with this architecture, we can now reload any amount of data into the HeatWave cluster in a fixed time, regardless of the amount of data you're trying to reload. The second thing is that since we now have this data stored in the object store, we store it or we place it in such a granular fashion that when we want to fetch the data, we can only fetch part of the data. We don't need to get the entire table back. So in this example, what we are showing is that we have a 4-node cluster, and let's assume there is some failure on one of the nodes. Well, when there's a failure, the system autopilot detects that there's a failure. It reprovisions a node, gets the node back, and it's able to reload the data. When it reloads the data, only the data of that specific node needs to be fetched from the HeatWave storage layer. The rest of the nodes can remain as is. And this is because the data is broken down into fine-grained chunks before being stored in the object store. Right? So the three things we saw are when we are fetching the data from the object store, there is no need for any transformation. The loading can happen in parallel, and only the chunks which need to be fetched are fetched, the rest don't. So now let's see what is the performance improvement we get. So what I'm showing over here is the various data sizes: 800 gigs, 2 terabytes, 10 terabytes, all the way up to 32 terabytes. What you're probably not going to be able to see very well is what is the time it takes now. Well, now it's about 4 minutes constant, regardless of the size of the data. In the past, when we are loading it from the MySQL database, the time would vary, right? So for the 800 gig case, which is the smallest cluster size, the time it would take us to reload the data would be 36 minutes. And for the largest cluster size, the amount of time it would take us is about 1400 minutes, which is close to 20 plus hours, right? So for the largest cluster size, the performance improvement, right, is from 1400 minutes down to 4 minutes, which is 350 times faster. Now, please note that the thing which you can see is the amount of time it's going to take to load is constant, regardless of the size of the data. But whether it's 4 minutes or 5 minutes or 8 minutes, this really depends about the amount of object store bandwidth available in a given OCI region, right? So this time may vary, but whatever the time is, it's going to be constant. So it may not always be 4. 4 is the number we got in some of the larger regions, but some regions are smaller and the object store bandwidth will be less. So there the time may be a little higher, but it will be much faster regardless, right, compared to the existing time, and it'll be constant time regardless of the amount of data we're trying to reload. The thing which I want to emphasize is this reload is a very important operation. We don't do reload anytime a query is run, right? So that way it's not as frequent as a query, but it is something which impacts the availability of the system. So if a node goes down, you're trying to recover the node on a 10 terabyte cluster size, right? It would take in the past 7.5 hours to reload. Now it's down to 4 minutes. So the availability of the cluster improved because the earlier the cluster would not be available for 7.5 hours. Now it's only 4 minutes. Similarly, when we are trying to do an upgrade, same issue over there. Right? That the availability of the system has improved dramatically. Many times people want to suspend their cluster and then restart. There again, the amount of time it's going to take to reload is significantly reduced. So this operation is something which directly improves the availability of the service. Now, please note that even when the HeatWave cluster is down for whatever reason or not available, the queries are still all being executed by the MySQL node, right? So your database is always up and you're still getting at least the MySQL performance, but it's this accelerator which would not be available when the system was either in the suspended state or there was an error, it was upgrading, or in the future when we have some profile elasticity. All of these operations now have a much, much improved availability. When we introduced the object store, one of the things I should highlight is that not only is the data stored in the in-memory format, but the data is also stored encrypted in the object store. Now, all along, since we have had the service, the data has always been encrypted at rest in the block volumes. Now, what you have also done is that all the communication is also encrypted. So for instance, all the communication between the HeatWave nodes and the object store, all the communication within the HeatWave cluster, between the HeatWave nodes, all of this is encrypted. So now customers who want to store the more secure data, because there's some class of data for which this is required, and many of the vendors make this thing as a default, but most of them don't. For most of them, there's a performance hit, so it's a choice which the user needs to make. In our case, security is fairly important, and as we are seeing customers store more secure data in HeatWave, we are also increasing the buffer security, so all the communication is secured and encrypted. Okay, so this was so far about the scale-out data management and what are we doing to improve the data management capabilities to make sure that they scale out well. Now let's talk a little bit about the query processing aspect of things. We support a larger cluster size of 64 nodes, which can process up to 32 terabytes of data. One of the many challenges which people face is that with larger data sizes or with larger cluster sizes, systems don't scale very well. This is one of the challenges, like in distributed computing. What we are showing over here is in the past we were supporting 24 nodes. Now we are supporting 64 nodes. And these are like the scalability results for end-to-end queries. That our scale factor, even at 64 nodes, is as good as it was at 24 nodes, which is as good as almost at 4 nodes, right? So whether you have 4 nodes, 20 nodes, 50 nodes, 64 nodes, the performance of the system almost improves linearly. The second thing which we have done, which is shown between blue and red, is that we have improved our scale factor further. When we went GA, as it is, our scale factor was pretty good. It was like about 0.81. Now we have improved it even further to 0.89. And note that 1 is the perfect scalability, which is very, very hard to achieve in practice. But this represents as to how efficiently we are able to use the nodes, even when the size of the cluster is large. And this is one of the reasons we get very good performance advantage when we compare with the competitive services. It's important now for me to recap a little bit about MySQL Autopilot and how it relates to this thing. So we introduced MySQL Autopilot, which provides machine learning based automation. So what we do as a part of MySQL Autopilot is that as users load their data into the MySQL database, as customers run their queries with MySQL HeatWave, the system has machine learning models which learn from the various aspects. For instance, they learn about the data being loaded into the memory. They learn about the query execution characteristics. And based on that, they either make a recommendation or they make a determination, for instance, in terms of coming up with the right execution plan. This is the only service which has this sophisticated amount of machine learning based automation. And I'm going to touch upon a couple of key features here. The first one is related to the change propagation for the scale-out storage, which I just talked about. So just to be clear once more, that the data from or any changes which are made to the MySQL database, those are propagated in real time into the memory of the HeatWave cluster. Right? So that happens right away. Like there is no logic or like there is no intelligence. It's like those changes will be propagated right away to the HeatWave memory because that is needed for running the queries. However, the propagation of this data to the object store, that can be delayed, that can be deferred because that's not needed right away. Right? That's only needed, for instance, when there is an error happening or when there's a restart happening. And also, you want to push in the changes at the appropriate time because you're writing it in certain format. So what we do is that instead of having a static policy that, oh, we're going to push the changes every so often, we have a machine learning model in the HeatWave and MySQL engine, which looks into a bunch of these considerations. For instance, what are the rate of the changes? What are the size of the changes? How many uh, times is it the case over the last 1 hour? For instance, has there been a need to reload the data? What is the object store bandwidth? So we have a machine learning model which factors in many of these variables, and based on that, on a per instance basis, it comes up with the appropriate or the optimal time to push the changes from the MySQL database into the object store. So this is again one of those examples that this is not a rule-based policy. It's a machine learning model. And this is being tuned or determined on a per instance basis. So that way the system doesn't push the changes into the object store too often, but at the same time, it does not do it too seldom, right? And that's why the combination of how frequently the changes are being made, how often do you need to reload the data, what is the object store bandwidth, all play a role over here. The second feature I want to talk about for Autopilot is the auto data placement. When the data is being loaded from the MySQL database into the memory of the HeatWave cluster, the way the data is distributed in the HeatWave cluster makes a big impact to the query performance, because we want to minimize data movement across nodes, because data movement over the network is expensive in terms of the latency. What we have with MySQL Autopilot is that based on the queries the user is running, the system makes a determination if the way the data has been placed is optimal or not for those specific queries. If not, the system makes a recommendation that how should the data be repartitioned. It will tell you the column name, and it also tells you exactly how much of an improvement the application is going to see if they adhere or if they follow that recommendation. No other system provides this level of information to the user, right? Which column to partition on and what is going to be the improvement expected if this recommendation is followed. The other feature of Autopilot is the auto query plan improvement. Here, as the user and the application runs queries, the system learns from these queries. It stores various kinds of metadata about the queries which have been executed. And then when a query comes in, the system sees if there's an opportunity for it to reuse some of the statistics of the information from the prior queries to improve the execution plan, either the logical execution plan or the physical execution plan for any of these new queries. And if so, it it uses information from the prior queries to improve the execution plan. And for TPCH and TPCBS on 24 terabytes, we found that this feature alone improved the performance of the aggregate benchmark by 40%. So the combination of all these improvements in scalability, as well as all of these improvements with Autopilot, result in a fairly substantial advantage of MySQL HeatWave compared to all the other services. So now I'm showing the comparison of 30 terabytes TPCH in comparing with Snowflake, Redshift, Synapse, Google BigQuery. What we find is HeatWave is the fastest service by far compared to any of these services, and also the least expensive. And the cost advantage is understated because, again, please remember that all of these analytics services, they most likely have a source database from which they are getting the data. It's a source database where the transactional processing is going on. Right? So significantly faster and significantly cheaper than all the services we have benchmarked against. And in today's presentation, right, I've shown you 3 workload sizes: 4 terabytes with Aurora and RDS MySQL. Then we show you numbers with 10 terabytes with Snowflake and Redshift on the latest version. And now this is 30 terabytes, which is a data size we can now support with the HeatWave cluster. Well, one thing is to say that a product or a service looks good in benchmarks, but what is also very interesting is to see what is the customer feedback and what is the customer adoption. Since we have gone GA in December, we have seen a lot of interest, and interestingly, there have been a lot of migrations from other clouds to MySQL HeatWave. So not only are we getting customers who are on-premise, who are running MySQL workloads, who are coming to the cloud to benefit from MySQL HeatWave, But it is also the case there are customers migrating from other clouds, primarily from AWS. And it is not surprising to see why that's the case. First, people can migrate from Aurora to MySQL without changing their application. It's API compatible. Aurora is API compatible with MySQL, so customers can very easily migrate their application. That's the number one. Secondly, what is happening is consistently across the board. Customers find the MySQL HeatWave is significantly better for their performance, and it costs much less. So in the case of Red 3, I moved about 6 terabyte workload from Aurora to MySQL database service in OCI. And they found that with HeatWave, some of the queries improve up to 1,000 times, but the net aggregate overall workload, which has a combination of both OLTP transactions as well as some of these complex queries, net aggregate improvement was 85%. And their cost, they saved 60% from Aurora compared from migrating from Aurora to MySQL HeatWave, right? So much faster, much cheaper, didn't require a change of the application. Another example is Tetris, same story. They had a combination of mix of OLTP and some complex queries, and what they found is that their query times dropped from minutes to milliseconds, and the cost again dropped to less than half. So this is one thing which was a very interesting observation, that most of the customers who are running their workloads in Aurora, it's really a mixed workload. They have OLTP, but they also have complex queries. They also have queries which take a while. And these queries improve dramatically when run on MySQL HeatWave. And the amount of improvement depends upon the data size and the complexity of the queries. But pretty much every single customer who has tried running a workload which was running on Aurora, MySQL HeatWave, has seen improvement in performance. The amount, the degree varies, and everyone has seen a reduction in cost. So these guys reduce the cost by half. Fan communications, very similar story. No change to the application from Aurora to HeatWave. Performance improved by 10 times with HeatWave, and the cost dropped significantly. Another one, Tamara. These are folks based out of the Middle East. Same observation, cost reduced by 3 times. Significant acceleration to many of the queries. And one of the things they observed was that now that HeatWave can accelerate many of these complex queries, which are taking much longer with the other products, they can have more interesting, more relevant application logic, right, running in their product. So they can do a better job serving their customers. So yeah, so this was a summary of the feedback from the customers. So to summarize, MySQL service with HeatWave in the Oracle Cloud is the only MySQL-based service which provides efficient processing for mixed workloads, OLTP, and analytics. Right? So it handles all your workloads better and faster. Secondly, even if you compare with the best analytics services out there, MySQL HeatWave offers the best price performance compared to Aurora, compared to Snowflake, Redshift, Google BigQuery, Synapse. For Aurora, for analytics alone, it is significantly faster. But even if you look at most of the real world workloads, right, which is a combination of OLTP and queries, and on much smaller data sizes, they're like, we're talking about 100 gigs. Even for 100 gigs, MySQL HeatWave offers 42 times better price performance compared to Aurora. 18 times faster at 42% of the cost. MySQL HeatWave offers machine learning based automation, which is MySQL Autopilot, which we talked about last time. MySQL HeatWave is the only MySQL based service which offers hybrid deployment, meaning that customers can have their primary database running on premise, and they can have a secondary instance running in the Oracle Cloud with MySQL database service, to which they can attach on HeatWave. So the advantage is that they can still run analytics on data which is stored on premise. And finally, this is the only service, MySQL HeatWave, which is provided, which has been developed, maintained, and managed by the MySQL development team. And there are lots of advantages of this. One of the very obvious ones being that you're always on the latest and the greatest version. For those of you in terms who would like to try the service, we highly encourage you to try the service today for free. You can go to this URL and get information as to how you can sign up for the service. And if you would like to get more details, please connect us in any of these like social media channels. And for a lot more details, including white paper, demos, customer testimonials, analyst feedback, um, a link to GitHub, please visit the website. So one thing I should highlight is that all the performance numbers I've shown, the scripts for those are available on GitHub for anyone to try on their own. So we encourage you to try on your own and see what the results look like. So with that, I'm happy to take any questions.